whenever we're trying to analyze some kind of situation in terms of energy, remember that energy is a property of a system. So the first thing that you have to be clear about is what exactly is in the system. What of all the objects that are described in the problem, which ones should go in the system, which ones don't need to go in the system. We've got four handy rules. The rules are described there in chapter 10, but the rules basically go like this. Any moving thing should be part of the system. If the thing is moving, then there's kinetic energy in the system. You want to take that into account. If the moving thing changes elevation, well, gravitational potential energy depends on elevation. So if the elevation changes, the gravitational potential energy must change. And if the gravitational potential energy changes, might sound strange at first, but you have to include the Earth as part of the system. The way we think of potential energies is that they're not a property of just one thing. They're a property of the whole system, or to put it maybe in a better way, potential energies are shared. They're shared by the things that are interacting according to some force. The Earth and whatever is having its elevation change are interacting by means of gravitational forces, and so that gravitational turns out we have to think of that gravitational potential energy as shared by the things that are, by both the things that are interacting, the Earth and the thing that's changing elevation. You'll see in a minute how that actually is a useful way to think. Any elastic object that's getting distorted, getting stretched or compressed or twisted or whatever, that means it's being given elastic potential energy, and so you'd want to include that in the system. Then, if there's friction, as I just said, if there's friction, that's going to increase the thermal energy of the objects in the system. And so it's surfaces that are feeling and applying the friction forces. So now you want to be sure to include all the surfaces that are feeling friction, because those surfaces will have their thermal energy changed because of the work that's done by friction. Let's see how this works in a specific example. So let's say you've got a firefighter here on the second floor of the firehouse, and an old-fashioned firehouse where you've got the pole that they slide down to get to the ground floor. And let's say the distance between the second floor and the ground floor is 10 meters. And the mass of the firefighter is 80 kilograms. And then slides down the pole. At the start, when the firefighter just jumps onto the pole, the firefighter has essentially zero velocity. But of course, the firefighter will speed up by the time they get down to the ground floor, and the instant before landing on the ground floor, there's some final velocity that isn't zero. Let's say that specifically, let's say that final velocity is 2 meters per second. And there's a lot of friction between the sliding firefighter and the fire pole. And it turns out that if that friction were not there, the firefighter's final speed would be much, much, much higher, because as the firefighter slides down, remember that the friction force on a sliding object, kinetic friction, always points opposite to the velocity. Firefighter's velocity is down, so force of kinetic friction points up, and anything pointing up would make the firefighter accelerate less and speed up less than would be the case otherwise. So in other words, a lot of the energy in the when everything is finished here and the firefighter lands on the ground floor, some of the energy is kinetic, but a lot of it is just becomes an increase in the thermal energy because of all the work that was done by friction. So, how much energy is gained by friction? And the way to start this is to not look for an equation that has this in it. First of all, you don't have to look. There's only one equation that has this in it. That equation. But don't start there right off the bat. Start first by understanding what's really going on, and when you understand what's really going on, then you can use that correctly. First place to start is, by this point this should not surprise you, the place to start is asking the same old question: what forces are acting in this case? And specifically, you want to focus on the forces that are acting on the moving thing, the firefighter in this case. So in that case, there's really just two. There's the kinetic friction force opposite to the sliding firefighter's velocity, and then there's weight. Since I now use W for work, I'll use mg, m times g for weight. Okay. This is an important number if we want to find this number. Remember, this is the net work done by external forces. So we have to first find the external forces, and then if there are any, we can see how much work they do. So look at all the forces you've identified and figure out if they're internal or external. This is an internal force because it comes from part of the system. We want the pole to be part of the system. Right. In this case, remember our rules. Moving things have to be part of the system, so that's part of the system, the firefighter. Rule number 2, elevation changes. So if that happens, gravitational potential energy changes, and we're going to have to include the Earth as part of the system. So 2 things in the system so far: Earth, firefighter, and there's friction. So anything that's feeling a friction force or applying a friction force has to be included as well. The pole is applying a friction force to the firefighter, and similarly, as Newton's third law tells us, the firefighter is applying a friction force to the pole. So this force on the firefighter comes from the pole, which is part of the system. And this force on the firefighter, the weight, the gravitational force from the Earth, comes from part of the system because we had to include Earth as part of the system. Whenever elevation changes, we have to include Earth as part of the system. But now, look at what's happened. the only forces are internal forces. There are no external forces. And since there are no external forces, obviously the amount of work done by external forces has to be zero. And since no work was done by any external forces, then the total energy of our system does not change, because work done by external force is the only way to change a system's energy. So, overall, the system's energy did not change, but individual types of energy did change. For example, the firefighter starts out with zero velocity and ends up with some velocity. So in other words, the firefighter started out with zero kinetic energy and ends up with some kinetic energy. So the kinetic energy increased. A positive change in kinetic energy. And the firefighter went from a higher to a lower elevation. The elevation decreased. And remember our equation for gravitational potential energy, mg times elevation. So if elevation decreases, gravitational potential energy decreases. Negative change. There are no elastic objects getting stretched or squeezed in this case, so nothing happens there. The elastic potential energy in this system is always zero. But there was friction, and friction always increases the thermal energy of the objects, or at least some of the objects in the system. So that's what we know. Now, the next part is to write out in detail all, zero equals a bunch of stuff, and we want to write out in detail that bunch of stuff. You're going to get the same instruction in some of the assignments, and it will always mean the same thing. When I say write out in detail, it's always going to mean the following. So total energy change is zero, and now I write out in detail the non-zero terms. Change in kinetic energy is, of course, final minus initial kinetic energy. Writing out in detail means if you've got an equation for that kind of kinetic energy, just use that equation. Don't just write K final minus K initial. Write out what K is in terms of mass and velocity. And then same thing here. Change in gravitational potential energy, don't just write it as final gravitational minus initial gravitational potential energy. Write out what gravitational potential energy is. Write it out in detail in terms of masses and g's and elevations. So final potential energy, mg final elevation, minus initial potential energy, mg initial elevation. And then that term is zero, so you don't need to bother writing it. And the last term is the important one. That's the number that we're trying to get. We don't have an equation for it, but we really don't need a special equation for it. Because this is our equation that will tell us what the thermal energy change is. Now, at this point, all we have to do is, we've done all the hard work. Now we just insert the numbers. The initial velocity was zero. So this whole term here, initial kinetic energy, is zero. The firefighter fell 10 meters. Here's the initial elevation, here's the final elevation, and there's a displacement of 10 meters. Remember, we can put the zero level of elevation anywhere that's convenient, and convenient would seem to be to put 0 here at the bottom and then let the positive direction be up. So the final elevation is 0 and the initial elevation is 10 meters. If the final elevation is 0, then this term is 0. So now we've got a much simpler equation. 0 equals this minus this plus this. So let's write that out. 0 equals 1/2 mass V final squared minus mg H initial plus thermal energy. Let's solve that equation for the change in thermal energy. That is, just do some algebra so that change in thermal energy is all by itself on one side of the equation. That is, add mghi to both sides of the equation. And then subtract 1/2 V final squared from both sides of the equation. Gives us the total thermal energy. So now let's put in the numbers. M, that was 80 kilograms. G is, of course, the usual 9.8 meters per second. And then H is 10 meters. And then minus the final kinetic energy, which is minus 1/2 80 kilograms times 2 meters per second all squared. And that's going to equal the total amount by which the thermal energy increased. Well, notice this is a pretty small number. 1/2 times 80 is 40. And then 2 squared is 4. So we've got 40 times 4, or 160 joules. Joules is the normal unit for energy, and to get our numbers to come out automatically in joules, we always must use masses in kilograms and distances in meters. So there's that. This, on the other hand, is a much bigger number. 80 times 9.8 is 784. 784 times 10 is 7,840 joules. So the total increase in thermal energy is 7,840 minus 160. Or 7,680 joules. So look at what happened here. In the initial state, before the firefighter started sliding down, there was this much gravitational potential energy. Only this much of that initial potential energy went into kinetic energy in the final state, and almost all of it, way over 90%, went into thermal energy. If this had not been the case, then the final kinetic energy of the firefighter would have been much bigger, corresponding to a much bigger speed before the firefighter lands, and the firefighter would be seriously injured when landing. Every energy problem that you see works exactly the same way, without exception. Do the same steps. Decide what's in the system, what things are in the system. Find out what forces are acting usually on the moving part of the system. Decide whether they are internal or external forces. Then look at the all those terms in the one equation. Work equals change in energy equals change in kinetic energy plus change in gravitational potential energy and so forth. Decide whether each of those terms is positive, negative, or zero, and then write out in detail the ones that are non-zero, and then you will have an equation that you can solve for whatever it is that you're trying to find. That's the way it always works every single time. So there are lots of ways in which the process could be difficult, but one difficulty that you absolutely should not have is trying to figure out what to do. You know what to do. You do those same things every time. Now, it may be difficult to do those things, but you know what you have to do.